Hello everyone, this is lecture 43 of PEC. Let's discuss small signal analysis of the nonlinear circuits. In the previous lectures, we have learned the analytical method, the graphical method, and the piecewise linear method for the nonlinear resistor circuits. So why do we also need the small signal method? There are two reasons. First, for such a nonlinear resistor circuit, as the figure shown, there may be a small disturbance in the circuit, such as a small disturbance of the voltage signal. How does the diode respond to this case? It needs to be analyzed by the small signal method. That is to say, we are interested in the response of the branch variables when there is a small perturbation in a nonlinear resistor circuit. This is the first case. The second case is that through the analysis of the circuit with a small disturbance, we can have a special design on the relationship between delta US and US. Then we can realize some specific function such as amplification. Next, we take a conceptual amplifier as an example to explain the meaning of the small signal. Look at the conceptual amplifier. What is it? By using the exponential properties of the diode, we add a sinusoid voltage to the diode. Because the exponential properties have significant amplification properties, so we can obtain a very large current. At the other side of the current, if we can get a current-controlled current source, then we are more likely to get a very large voltage for the load. So we may realize the exponential amplification from the source to the load. Let's take a look at it. Is there any problem? The UI characteristic curve of the diode is given in the figure. We add the sine voltage to both ends of the diode. We can draw the waveform of the sine voltage varying with time. Then we can get the output current a point by a point. Because we know the load side is a linear current-controlled current source, that is to say the voltage of the load is directly determined by the current here. We take a look at the output current of the diode, whether it is an amplified current or not, along with the input sine wave. Look, we also draw the time axis of the current. When the voltage is zero, the current is zero because it's a resistor. When the voltage is a certain value, the current is a very small value and it's close to zero. The time is same, it's almost close to zero. As the voltage increased gradually, the current is increased a little from zero. It has increased significantly when the voltage is here. When the voltage is the maximum, of course the current reaches its maximum. If time continues to increase, the voltage is reduced and the current is also reduced. When the voltage drops below a certain value, the current is changed to zero. When the voltage is in the negative half cycle, the current is almost zero because of the nonlinear UI properties of the diode. By connecting all points, we can get the current waveform like this. Comparing to the voltage waveform, the current waveform looks a little bit like a half-wave rectification. Moreover, because this is an exponential form equation, the waveform has obvious distortion. We are not satisfied with this result. Here I have a question. why the conceptual amplifier we expected couldn't come true by a nonlinear element with such a UI feature?